We're going to finish off talking about probabilistic programming. It's the last lecture of this wonderful 2 weeks. So far, we've talked about various aspects. In the first lecture, we had a quick high-level summary of what you can do in the general purpose probabilistic programming. And then yesterday, we did 2 things, quite different things. One was that we looked at ways of making inference algorithms that work, that you can experiment with different models. And then we looked at some more mathematical aspects of the whole thing, which is how to give a mathematical meaning to probabilistic programs. And we saw that measure theory, which is a way of formalizing probability theory about 100 years old, doesn't really work with higher order functions. And a new thing that I've come up with Chris Hoyne and Kamar and probability spaces works really well. So what I want to do today is to look at another aspect of probabilistic programming that I find really exciting, which is suggesting new complex statistical models. So the title of this course, I included the word non-parametrics. I want to get to non-parametrics in the second half of this lecture, but in the first half we're going to be parametric. Remember, in statistics, parametric is easier than non-parametric. And I'm in fact going to take us back a very long way, like about 100 years, okay? In this first half of the lecture, and in the second half, we're going to use those ideas that are 100 years old or a bit less, and see what's happening right now in some aspects of statistics and learning. Before I do that, then, let's switch over to Emacs. I just want to come back to a little idea that we talked about last time. I took this program, which was a random linear function, and I switched the lines around. And I said to you guys, can I switch the lines around? And you all said yes. And then I said, well, actually, the inference, it's not quite clear in the way that the program's represented to the inference algorithm. That's true. There's a little bit of thought that needs to be done. But in the mathematical model, it's hopefully crystal clear that you can reorder the lines of the program. So we can reorder the lines of the program. What if I do this? Is that okay? Have I changed the meaning of the program? I just inserted an extra line where I drew another sample from a normal distribution. Who thinks that's changed the meaning of the program? Who thinks it hasn't changed the meaning of the program? Okay, anyone want to say why they think it hasn't changed the meaning? Because the C is not used, yeah, right. So in programming language, sort of terminology, we could do dead code elimination and get rid of that line. Can I always do that, by the way? If I'm programming inside a do block here, can I always just get rid of lines that don't seem to be used? Who thinks yes? Who thinks no? Okay, when can't I get rid of lines that can't be used? Yeah?
But are you doing something interesting behind the scenes?
Yeah, I think it's doing something interesting. But yeah, so give an example of an interesting thing that would mean that I couldn't... sorry? I.O. If I was doing I.O., if I printed something, or if I read something from the console, then I wouldn't be able to get rid of that line, yeah? Even if I didn't use the result. So if I read something from the console, I don't use the result, doesn't mean I can delete that. So something very special about probability that's embedded in your intuition about probability says I can reorder the lines of the program and I can throw them away. And I think that's closely related to a sort of philosophical concept in statistics, which says if I want to study a group of people, I can move them around, I can reorder them. It doesn't matter if I throw some of them away or keep some. In other words, I can treat them all as if they were exchangeable. So exchangeability is a crucial concept in statistics, and I think it's really connected to this idea of being able to reorder lines of programs. I call that commuting lines, and being able to discard lines of programs. One last thing, can I do this? So now, the mean of the second normal sample depends on the first normal sample. Can I now reorder these lines? Who thinks yes? Who thinks no? Yeah, okay. So no, and maybe Haskell will leave a complaint, it doesn't know what A is. So I can only reorder the lines of a program as long as the data flow is respected. So now to illustrate that point, I want to play a game. Well, I said game, I mean it's something that's fun, but it's not something you want to do. Are you involved in it? So what are you thinking about whether you want to volunteer? Let me tell you the rules of that. I've got red cards and I've got black cards. I'm going to start out with a red card and a black card in my hand. And in each round of the game, these are the rules. I draw a card, or actually one of you is going to draw a card, and I put back two things of cards of the same colour. Two cards of that. So I'm going to start out with two cards in my hand, and the number of cards in my hand is going to change. Okay, so now you see it's not a very dangerous game. Does anyone want to volunteer? Don't leave me hanging. Who's on a scholarship? Oh, yeah. Okay, so I'm going to start with two cards. Okay, a red one and a black one. Can you pick one? Okay. Show everybody. It's a red. And I'll put back two reds. Show everybody. Another red. Take two reds. Another red. Let's do one more. Okay, just open it. So another red one. So how many cards have we drawn? Four cards. Okay, all of them red. Oh, we're going to put back. Sorry, we're going to finish the rest. So that's what my hand looks like now. It's got one black card and I guess 1, 2, 3, 4, 5 red cards. Now I want you to have a guess. What's going to be the rate? We could keep on playing this for a few minutes, so let's pause it. I'll just give you a round of applause. What's going to be the ratio of red to black cards in the limit? Who thinks we're going to end up with all red cards? Who thinks we're going to end up with a black card? Has someone got another idea what ratio we might have? So start thinking about it. I just want to do one more draw. Yes, I'm going to do one more draw. Sorry, can you come back? I'll do two more. So do one more draw, but don't show anybody the answers. So you guys are probably guessing what it was. I'm going to put back two copies. Okay. So now what he's done is, and now throw that card down to throw it. So we've done another round, but then he's thrown that one away. That corresponds to dead code elimination, adding another line and then getting rid of it. Does that change the statistics of everything? Okay. I got one extra card in my hand now, but can I just carry on? Or does it matter that he threw that card away? Anyone think it matters that he threw the card away? Anyone think it doesn't matter? Okay, somebody thinking it doesn't matter. Let's go through a little calculation. So you don't know now what's in my hand. I know that there are some red cards. You know that there are some red cards and black cards. But you don't know exactly how many. Let's do a little calculation. So you've seen R red cards and you've seen B black cards. Then at the draw that we discarded, the chance of getting a red card was quite high. It was R over R plus B. You get red cards out of the number of cards altogether, chance of getting red. On discarded draw. Yeah, sorry, I'm going to hit. Okay, So now in my next draw, I don't know what the ratio is. Either he drew a red, in which case the chance of getting, so what's the probability of getting a red on the next draw, the subsequent draw after we discarded it? Well, either he drew a red that time, in which case the probability of getting another red is r plus 1 over r plus b plus 1. Or he drew a black, in which case the probability of drawing a red again is r. That's the probability he got a black in the discarded draw, and that's the probability of getting red in the draw. Let me simplify this. R times r plus 1 plus rb over r plus b plus 1 times r plus b. Simplify it. R times r plus b plus 1 over r plus b plus 1 times r plus b. And now I can cancel r plus b plus 1. And I end up with r over r plus b. So in other words, whether we don't know what's in the hand, whether he discarded a red card or a black card, doesn't matter, as long as he and nobody else ever looks at it, doesn't matter, because in either case, we end up with the same ratio of r to r plus b, which is the same as the probability on before we made the discard. Okay. Now, in general, if we have a programming language which uses state, memory, and we start writing to memory and changing our memory, then we can't discard things, and we can't discard things. But in this particular example, it's very carefully constructed so that it is okay. It also, we could go through a similar calculation to say it was okay actually to commute draws. If you made a draw, didn't tell you the result, did another draw, and then swapped the results around, that wouldn't change the So playing this game, playing around with this game, behaves a bit like probability in the way that we can commute the draws and we can discard the draws. This game was invented by Polya, back, I guess 100 years ago or more, to illustrate this kind of interesting. Anybody got an idea yet what kind of, if we kept on going, what number we'd get to? So what we could do is write a program. Oh, so you got an idea?
Well, I was thinking if it's the same, it's going to be the same as the first time. That was
Yeah, okay, so you think it might be that we've been very unlucky and got lots of reds. In the end, we're going to end up at 50-50. No, it's good to guess, it's good to guess. Well, not in an exam, but this is. So we could keep playing. So let's write a program to do it. So I've written a program. I call it Polygon. So I'm not going to use, for most of today, my Haskell monad Mantropolis Hastings because I've got memory around, so it's no longer. I'm just going to use the IO monad as if it was a monad of probability. Okay, so where's this? Okay, yeah, so I've just typed it up. So kicking off a new card game means initialize a new piece of memory with one red card and one black card. That's how we started, one red card and one black card. Here's a little bit of code. I don't know how quickly you can read code, but it explains these rules here in. And so what I've got here is an IO ref, that's a pointer to memory, which is remembering what's in my hand. And so as the game progresses, I either have more red cards or more blue cards in my hand. And then I could run this program, I could run it, I mean, we only managed 4 lines and it will still already start getting a little bit boring. We could run it very quickly on a computer, I think I did 10,000 runs or something. So I did 10,000 runs and I looked at what the ratio of reds to blacks was going like over those 10,000 runs. And then I started again. I ran it all the way and looked at what the ratio of reds to blacks was going. So I did it. I did 100 games, and each game I did, I think, about 10,000 runs. And then I looked at the ratio of reds to blacks, and I plotted them here. Okay? They're falling uniformly across the unit interval. So an amazing theorem about this game is that if you play it for a very long time, you end up with a sample from the uniform distribution of the unit input. Just to illustrate, maybe you think there's a pattern here, and you played it 100 times, let's play it 1,000 times. You see it's really a flat line, uniformly distributing numbers, the ratios, across the unit input. In fact, so this is a little module, right, where I say new, that means kick off a new card game, and I say get. I can make another, I made another module, which I call uniform, which is the same interface. Can you see it has the same interface? Yeah. It's got a process, it's got new, and it's got get, but a totally different implementation. So now new, which fits on this screen, new draws a uniform number between 0 and 1, and get does a Bernoulli trail, tosses a times trail. So rather than the process being appointed to memory, storing how many red and black cards are in my hand, the process is a real number. And these two modules behave the same. I've used a bit of module stuff, a bit of hiding to make sure, because when you start inspecting what the double is, then they're no longer the same. But if we hide things in this way, these two modules behave the same. I still, I mean, I've been thinking about this for 3 or 4 years. I still find it really surprising. In one case, we've got memory going on. In the other case, there's no memory being used at all. Or no, at least no explicit reference says mutable state. The first case, we've got mutable state. The second case, we haven't. The second case, this one, we're doing draws from a uniform distribution on the unit interval. To understand what that really means, you need to use measure theory or something like that, as we talked about last time. The cards implementation, there's no measure theory needed, it's just a coin toss. That's what you need to do. That's the only point where parameters comes in, it's just a coin toss. So somehow, this memory pointer is the same as a real number. Yeah. So what do I want to say next? Yeah, let's look at one more implementation, which is very similar to the uniform. So I just changed it very slightly, so that now a process isn't a double, it's not a number between 0 and 1, it is itself a probability on the booleans. Well, it's not so ridiculous, because probability on the booleans is the same thing as a number between 0 and 1. If I've got a number between 0 and 1, I can turn into a probability when I'm just a coin. And if I've got a probability on the booleans, well, there's some chance of true and some chance of false. So that's also the number between 0 and 1. Okay, so this implementation is very similar to the other uniform implementation. So I start off and pick a number between 0 and 1, and then I return this probability distribution, which is the Bernoulli distribution. And then when I call get, all I'm doing is independently sampling from that probability distribution. In fact, there's a very general theorem about when this sort of thing works. So let me define this idea more carefully, this idea of commuting and discarding lines. Let's find it more carefully. Definition. A module is exchangeable. That's not a line back, that's the thing we're defining. If client, this is a bit informal definition. If the client can commute and discard calls to it, so in this case to new and get, without changing So when I've got a probability, sort of standard probability library, I can commute and discard calls to that without changing the result. You all have an intuition about that. But when I switch on to that's you're probably quite happy as to I can discard and commute calls to new and get in this case because there's no state around, there's just uniform distributions and vanilla distributions. But when I come to this case here, there's a bit of work to be done, and that's I did that sort of calculation, there's a bit more calculation to be done to show that I can actually also here, when I'm using this module, commute and discard calls to this module. So now I'm ready to state the theorem. This is the theorem due to probabilistic differentiality from 1931. If a module with interface new and get is exchangeable in the sense over there, then it has a state-free implementation. So obviously in 1931, Differentiality was not talking about abstract types and modules in Haskell. So what I've done is I've taken Differentialty's theorem, which is really about exchanging sequences. So if I have a module, I can call it lots of times and I'll get a sequence of results. And Differentialty's theorem was about the sequences of results. Now, if I translate his theorem about the sequences of results that you get, which we've gone forever, then I end up with this theorem about exchangeable modules. When I say state-free, I mean an implementation that doesn't read or write to mutual memory. So, I have to admit, when someone first explained this theorem to me, I misunderstood what they said, but I thought it was called a divinity theorem. It does kind of feel like we were playing this game of cards, and you can think of that hand I have. Yeah, you can think of that hand I have as a real number. And if you don't look inside it, it kind of is a real number, but we just don't, I don't know what it is yet, you don't know what it is yet. Right? But you don't need to know that I don't know what it is yet. Because if we just keep playing, you'll gradually learn more and more about the real number that it might, or at least what it might be. So it's kind of like, to understand this as a real number, you'd have to be divine, to see into the future and see what real number it was going to converge to when you learned. So I wanted to prove that these two modules were the same using standard techniques for program equivalence. You've seen, I think, with ML, or maybe with some other courses, ways of proving that programs are equivalent. But I haven't been able to, so if any of you want to have a go at that, you could try. And the reason being, informally, that to understand why these two modules are the same, I have to run all the way into the future to infinity. In fact, let me say a couple of words about how I managed to show that they're the same again. I wrote down all the program equations I could think of involving new and get. This program was about. Well, there's all the equations saying it's got to cause to commute and to new and get. I've got to commute, and I could be able to discard them, those equations. And then there's one more equation called conjugacy, which I won't talk about now, but it's a really important concept. And I couldn't think of any other equations. And then a new PhD student, Dario, started, and I said, can you think of any other equations? And we managed to show that if there was another equation, it would be inconsistent with the whole thing. So it's a very strongly complete theory. If I write down the commutativity and discardability equations, plus an extra equation of conjugacy, there can be no further equations. Therefore, to show that two modules are the same, I just have to show that they satisfy the commutativity, discardability, and conjugacy laws, which is very easy. In the stateful case, it's a little bit interesting. If you wanted to do it formally, you use a program logic, perhaps. Archie Shimshak did that. In this case, it's just a primary FPS measure. So before we take a break, let me just ask one more question. What if I'd started with two red cards and two black cards? So I started my game with one red card and one black card. Now if I start my game with 2 red cards and 2 black cards, the Fibonacci theorem is going to say that that also has a state-free implementation. What is it? So if I run this game through, I'm not going to end up with uniformly distributed ratios across 0 and 1. In fact, I end up, and just for fun, there we go. See? The mean is still about half, so a half was not a bad guess. But it could be anywhere in between. It's more likely to be in the middle. In fact, if you've got the density function of this probability distribution on the unit interval, it looks a bit like this. But anyway, that's what the density function looks like. Just a scale. And this distribution is called the beta distribution with parameters. I think we start with parameters from. I can't remember the parameterization. So, by choosing different number of starting cards, we get some very important distributions on the unit interval beta distributions. So that's what I wanted to say in the parametric case. And let's have a break now, and then when you come back, we'll talk about the non-parametric. Let's carry on. What we did in the first half of this thing was to talk about stuff that was going on just under 100 years ago. This little card game, actually, Collier described it in terms of an urn. You know, an urn is like a big bowl, and he had balls inside it. I was thinking of bringing that, but then I thought airport security might have some. So I brought it back in cards. Yeah, so now we want to take the idea of exchangeability, and it's coming up here as a very natural programming concept that everybody who's done programming languages would know about. Reordering lines and checking when that's okay. Dead code elimination, when can we get rid of that? And then understand that as a fundamental idea in building models of statistics. Actually, before we start looking at real sort of difficult model, it's probably something mathematical. Let's look at a real example. So I, last year, was involved in a little seed project with some social scientists looking at political hate in the UK. And we wanted to see whether we could use probabilistic programming to help them. It's really interesting to see the way they come at questions and the way we come at questions. So we got all the hateful tweets from the run-up to the 2017 UK election. And here I've plotted a dot for every UK politician, or one of the politicians, for everyone who stood in the election. And on the y-axis we have how many votes they've actually got, or what proportion of votes they got in the area. And on the x-axis we have how many hateful tweets they've received, or whether the target is equal. No received. Or the target. This is a log scale, so it goes about 10,000. We used a classifier, maybe we lost a lot of hate. People seem to think there's a lot of hate.
How did you classify them as hateful?
Yeah, right. Actually, it's quite scarring to look at some of the really horrible stuff. So anyway, what was I going to say? Oh, okay, yeah. So I drew this plot. Social scientists actually were not I'm not sure if this is right. But let's look at it for the illustration. By the way, in the UK, we have a first-past-the-post system, which means that you don't have to get the most votes to get in. You just have to get the most votes out of people standing in your area and in your constituency. And so, well, can anyone see any patterns here, any clusters? How many people can see 2 clusters? Squid. Yeah, how many people see 3 clusters? 4? 5? Okay, I mean, some people might see 1,000 clusters, right, one for each point. But we seriously want to answer the question, how many clusters are there? We don't know. That's a non-parametric question. If I say I think there are 2 clusters, then it's a parametric question, because I'm looking for the 2 clusters. Anyone guess who these 2 guys are? Or these 2 people are? Sorry? Maybe you don't. These are the leaders of the 2 main parties, Theresa May and Jeremy Corbyn. I can't remember which one. Yeah, so we could look at these clusters and we could make up a story. These guys are the ones who didn't get many votes, but some of them were very visible still. And in the UK, we get a lot of single-issue campaigners, and they'll stand for election just to get some media coverage. So, for example, the UK Independence Party, now the Brexit Party, they didn't win. I think they won 1 seat in the general election, but they fielded a lot of candidates, and they scored a lot of hate. I mean, maybe that's why Brexit is perhaps going to happen, right? Because those people don't have a say and they don't have a say. Anyway. Right, so there's 2 clusters. Now what I wanted to do was I decided to write a probabilistic program to try and figure out where the clusters were. So I did that. It's an interesting program. It's about 15 lines, a bit longer than the kind of programs we've seen so far. And then I could use it to draw some simulated partitions. Can you see the red and blue here? Yeah. So I wrote my program, then I said, okay, give me 100 more politicians. Just to check that it was all working right. And here I am. So in among that probabilistic program, which involves all kinds of stuff, one of the things that I've done is to say, I'm not sure how many people are in each cluster. I don't know if half the people are in one cluster and half are in another, or 90% are in one and 10% are in the other. And so what I have to start with is a flat distribution on a unit interval saying how many people, what proportion of people are in one cluster. So when a synthetic politician comes along and wants to decide whether he is a mainstream guy or a single issue guy, then he needs to draw from whatever the ratio is. So then when I run my inference, I end up with a better idea of that, and it's going to be some kind of curve like this that says that, okay, maybe most probably the ratio is whatever this is to this is 3 to 7 or something, but we don't actually know. We still don't know even after running. So I do that by using this game, or this card game. When I start off not knowing with a uniform distribution what the ratio of people in clusters is like, and then each time a single issue politician comes along, I add a red card. Each time a general general politician comes along, I add another card, and they keep going until I've got 1,000 cards in my hand, and then to figure out the next politician, I just draw one of those cards. And when I'm doing that with the synthetic politicians, then my hand gets bigger and bigger as well. So it's a useful way of programming. And because there's no state there, there is state there, because there's no real numbers there, you can actually do things symbolically. You can do an update, just changing what's in your hand, much easier in that circumstance. So Andy talked about message passing. That's part of the essence of the message passing algorithm. Okay, so now I want to push beyond this parametric idea. We're saying there's 2 clusters to say, I don't know how many clusters there are. So let's start with changing the game a little bit. I'm going to play the same game, but if I draw a joker, I pick a new colour and put that to a left. So actually I can start off with just a joker in my hand. It's a joker. And then I draw, I wonder what I'm going to get. I get a joker. And then I pick a new colour. Which should I pick, red or black? Good question. Let's pick red. Okay. And now in my hand I've got a joker and a red. I draw. I get another joker. I'm going to put a black in there. And now I've got a joker, a red and a black. The cards and I draw. And I get a red. I'm going to report the red. Sorry, I've already reported 2 reds. I'm going to have a black. And then I put in 2 more reds. Okay? So we play the same rules, but now with a joker in the hand, and if I pick another joker now, I've got to find another colour. Well, I only have red and black here, so we better stop. But maybe I'd add a green card. No, unintended. Okay. So one issue here is which colour should I actually pick? When I say pick a new colour, which colour should I pick? So I picked red to start with, and maybe I'll pick black. Maybe I've got like a linear order on some colours, some countable number of colours, so I just pick them in that order. The problem is if I do that, will I have an exchangeable module? colours in a prescribed order, will I have a given rate? Who thinks yes? Who thinks no? Yeah, the answer is no, because I'll always, if I look at what the state of affairs after one draw, I'll always have just a red card in my hand. There's no chance that I'm going to end up with a green card if I just have one draw. So statisticians puzzle over this, and they want to know how to represent colours. So what they do is they represent colours by real numbers. And when I say, pick a new colour, they say something like, they might say, here's the thing that they often say, sample from a uniform distribution. And that gives me a colour. And now I'm going to put my politicians in clusters according to which kind of ratios I've seen. It might be 2 clusters, might be 3 or 4, and I'm going to label those clusters by colours. And now those colours are real numbers, and so the names of the clusters are real numbers. So I want to know if 2 people are in the same cluster, I have to compare whether 2 numbers are equal. So they're always doing that, they're comparing whether 2 real numbers are equal, and they're quite happy to do that. And we know that that's a bit of a dangerous thing, it's a bit of a strange thing to do, but that's what they do. I would suggest, rather than calling the colours real numbers, let's have an abstract type of colours. An abstract type of colours where we can't look at the order of colours anymore. We just have an abstract type of colours and we can say, give me a new colour, and it will give me a new colour. But let's say we can't look at whether that's the same, whether that's comes before the other colours or after the other colours. So we use colour. Why not use Jensen? Simple generation. In fact, in the church programming language about 10 years ago, they advocated using Jensen quite a lot instead of using rules. Okay. So yeah, so I implemented that. Let's have a look at what it looks like. It looks very similar to what we did before. Oh yeah. Before we tell you what it's called, let's talk about a slightly different view of it. So this process with the joker in the pack is sometimes called the Chinese restaurant process. We're only about talking about restaurants at lunchtime, and it's not like any restaurant I've ever been to. Maybe you know restaurants like this. Chinese restaurant process. I'm telling you that in case it gives you a better intuition. So new gives me a new restaurant. We've got it up. So new gives me a new restaurant, and then get is going to give me a table in the restaurant. So the idea is, I've got a restaurant, start with there's nobody in there. Someone walks in, they sit at a table. The waiter lays out another table. Someone else walks in, they're going to decide whether to sit here or there. With half a chance they'll make friends with the guy here, or the girl, and with another chance they'll sit on a new table by themselves. Now someone walks in, the waiter lays out a new table. Now someone else walks in, with a third chance they'll sit with this person, with a third chance they'll sit with that person, and with a third chance they'll sit there. Because they sit here. And now there's still a 3 tables. So now we've got 1, 2, 3, 4. With a quarter chance they'll sit here, with half a chance they'll sit here, and with a quarter chance they'll sit here. So as I said, it's not like a restaurant I've ever been to that people just sit randomly with other people. Maybe everyone in this town knows each other. Some people talk about preferential attachment. As things go on, you're more likely to sit with on a bigger group, with a bigger group. So here I've implemented that. Is it worth looking at that? Probability on, okay, so in this situation I come in and with a quarter probability I sit here, with a quarter probability I sit at this new table that no one's at, and with a half probability I sit here. What you can do is actually change this this probability of sitting at into a fresh table, and that will give you slightly different. So now if we do the thing about something from a uniform scheme as a colour or Jensen, we end up with a module that is extremely common. And so to Finetti's theorem holds, all of this is stateful. As the Chinese restaurant runs, there's a state of the restaurant, which is the number of people sitting at different tables. But the theorem holds, and so there must be a state-free implementation. Let me tell you about the state-free implementation. It's a very simple program that generates, so we need to give a new and a get. So new, just as before, new is going to do all the heavy work in the stateless version. The stateless CRP, which is called stick breaking. And statisticians don't know the concept of laziness, but it's really about laziness. So I need to do new, and what it's going to give me. It's going to give me a list of real numbers this time. And the idea is it's going to give me a list of real numbers, and that's looking into the future at how many people are going to sit at the different tables in the limit. And it's going to be an infinite list, usually, because there's going to be an infinite number of tables. And so it's going to tell me the ratio of people sitting at the different tables in the limit. So I build that by taking the unit interval, 0 to 1. That's with stick breaking, because we think of it as a stick. And then we uniformly pick a point on that stick and just snap it. Point. And then we do it again. We pick a point in here. 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 Something like that. And we keep going forever. Okay? So we end up with a stream of real numbers. And now what does get do? So imagine I managed to break my stick all the way to infinity. In practice, we could be lazy about this. We could just wait until we actually need to know where the stick is broken before we actually break it. But when I want to know these different bits of the stick correspond to different tables in the restaurant. Get all the different colours of cards. These correspond to different tables. But I've done this all at once, and there's no state. This is just what we pass out. Now, when I say get, I need to know which table I'm going to sit at. What I do is I pick a number between 0 and 1 uniformly, and that's going to point somewhere on the real line, and that will tell me which table I'm going to sit at. Yeah. So I pick a number to get, I just pick a number uniformly. And I see which bit of the stick I now know. Do I land? Very easy technology to write it. It's a recursive program. Actually, we need to, I think I haven't been quite careful enough with the laziness here. But, so all get does is draws uniformly with a random number and then looks for which bit of the stick I should be in, and then returns that as the table that you should be in. So each customer comes in, we just randomly choose. This is a stateless implementation of the Chinese restaurant process for that card game. Any questions just now? Yep.
I'm not sure I understand how that's the stateless version, because, I mean, here there was a smaller chance of picking the table to the left as the first table.
Yeah.
But here it seems, I mean, if it's sort of in the middle, then
Yeah.
it's never going to
Yeah.
cut out.
Yeah, I don't know. You're interested. I mean, remember, when I break the stick, I draw an infinite number of uniform choices. So it's maybe not so easy to go intuition for that. Any more questions? Yeah, so because we managed to make the thing exchangeable, then we're able to recover, by de Finetti's theorem, an implementation that's stateless. Yeah, so let me say, people then started to make more interesting processes. This is sometimes called the trade process. And it's useful then, if we're doing clustering, we don't know how many clusters we're looking for. So it's a non-parametric method which is going to find some number of clusters within the data. If the data is finite, of course the number of clusters will always be finite because it's bounded by the number of people. We can go beyond though to look at even more crazy models. So for example, people came up with the Chinese restaurant franchise. Sometimes I like. And the idea is you've got some franchises of restaurants, different franchises, and each franchise has a number of restaurants. And each franchise also assigns certain dishes to different tables. So now there's 4 things to worry about. We walk it, we pick a franchise, we pick a restaurant that's in that franchise, And then we walk in there, and we pick a table, and we don't get the table, we find out what dish we've got. There's going to maybe some correlation between the dishes in the different restaurants in a given franchise. So anyway, so people could start making more and more crazy distributions like that. There's an Indian buffet process, an Indian buffet franchise. I don't know if there's a Pan-Asian franchise. So, yeah, so I thought, well, the Probabilistic theorem doesn't immediately apply here because it's not just new and get, there's some extra stuff. So what we need to do is update the Probabilistic theorem. But before doing that, I wanted to look at another interface we might have. So here's a random graph interface. I can say, give me a new graph, and then I can say, give me a node in the graph, and then I can ask whether there's an edge between two nodes. Let me show you an example of an implementation of that. I won't show you the code, I'll show you a picture. Always a bit of code to get this suited. Okay, so when I say get, I'm going to pick a point on the sphere. Let's pick a dimension. 3 to 3D spheres. And then when I ask if there's an edge between two nodes, the answer is going to be yes if the edges are in the same hemisphere, if the nodes are in the same hemisphere. Now if I get two nodes on the sphere, and I ask whether there's an edge between them, it turns out the probability of that is going to be 100. If I pick 3 nodes on the sphere, and I ask what's the probability of them forming a triangle, this might do if you're doing some geographical modeling. I ask if these nodes form a triangle, I wonder what's this probability? What's the probability of drawing 3 nodes and they form a triangle? And what these guys, probabilists, combinatorists, were looking at was understanding how we could look at these statistics and figure out the geometry of space where the graph is. But an interesting thing I thought was that as the dimension of the sphere gets bigger and bigger, this probability of picking a triangle converges to 1 over 8, which is just a half times a half times a half. So as the number of dimensions goes to infinity on this graph model, we end up with a random graph called the Erdos-Renyi graph. Now the Erdos-Renyi graph, so sorry, this is an implementation of Stateless. Okay. The Erdos-Renyi graph, we pick 2 nodes, and then we say, is there an edge between those 2 nodes? And it will just say yes or no with half a chance. There's no geometry involved, there's no correlation between the edges. Which I suppose is maybe an intuition. As the dimension goes to infinity, you lose all the idea of the geometry constraint. So here's a way to implement Erdos-Renyi, but I used state. So now when I say give me a node, I just pick a number. Between 0 and 1 or between 0 and 2. And then when I say is there an edge from P to Q, in the Erdos-Renyi graph, the answer is, well, either yes or no with, let's say, half a chance. And I'm going to need to remember what I said last time, because if someone asks me again, is there an edge from P to Q, I better say the same answer. First time I say, yeah, there's an edge from P to Q. Second time someone asks me, I better say the same thing. So I need to memorize what happened. So memorization seems incredibly important if we're going to prove a Probabilistic theorem like this for arbitrary interfaces. So Probabilistic theorem works for modules involving new and get, but to push it towards modules involving other interfaces, I believe we need memorize. And the problem with memorize, it's easy to implement memorize. You could in Haskell you could use unsafe before I you just remember what you called so far, right? Computationally memorize makes perfect sense. But I don't know any mathematical model of memorize. Okay. So that's what I wanted to say about pushing towards a general notion of exchangeability and a general framework for non-parametric statistics. So my conjecture is that there is a Probabilistic theorem for arbitrary module interfaces. And we have started proving some theorems towards that goal, for quite crazy hierarchical structures with like many, many layers and so on. But we still haven't quite finished that work. We have a paper about hierarchical structures, but the thing about memorize is something very So I want, any questions about that? Because then I'm going to come back and recap the course. Yeah.
So right now we don't have a uniform way of finding an implementation of a stateless counterpart of a process.
Well, I think if we can use memorize, we sort of, so in the graph case, there's something called graphons, which are very hot in machine learning years ago. And we can use those, as long as you let me use memorize, I can use graphons and a semi-canonical stateless implementation. We're still using memorize, so at the moment. In fact, I know for sure, well, so Cameron Breer told me for sure that I surely have to use memorize in the training. There's no stateless. Yep.
Isn't that one has to use memorize and the mathematical description model still has to be developed, or is it that memorize is a wrong abstraction? Is there maybe some kind of mathematical effect action on a description of memorize that would fit?
Yeah.
Because what you're saying suggests that this is kind of the only universal of abstraction.
Yeah, that's my hunch. Yeah. It would be interesting to see So I was looking for like a measure theoretic description of memorize, which but yeah, even a Dijkstra and something like that would be interesting. Because you want to know, I mean, memorize is very special, right? Normally, in a pure language, memorize doesn't have any effect, doesn't change it. In the probabilistic language, you see here, memorize is going to remember what the probabilistic draws were before, and so it is changing the behavior of the model. But it's still retaining exchangeability. So if you use memorize, you can still commute and discard. So memorize doesn't interfere with commuting and discard. Yep.
So it makes sense that the goal is to try and improve exchangeability for a larger and larger class of probabilistic programs. But can you comment on once you know exchangeability, what's the goal of then using that fact to do different things? Like you mentioned dead code elimination, but are there other kinds of passes or transformations or theorems you get once you know exchangeability?
Yeah, well, you have the two transformations here. You can reorder lines and you can discard. Yeah. You could also, I guess, go towards the stateless implementation. If some naive user wrote down a stateful thing, you could maybe go automatically to a stateless thing. Or the other way, you have a stateless thing which is inefficient because it's using lots of randomness, and you're going to have to do Metropolis Hastings to do the observations. If you use a stateful thing, maybe you can do the observations in a more symbolic way and avoid some of the overhead simulations. So, but that's going to be quite heavy to do that automatically. So I talked to Frank Wood about this, and then sometimes he says, well, maybe we shouldn't worry too much about exchangeability. We let people write stateful programs. And I saw a paper earlier this week that just came out and said, maybe we just care about exchangeability up to some closeness, up to some small distance. It doesn't really matter if it's perfectly exchangeable, maybe it's still. So this is some interesting ideas there. Yeah.
Could you expand on the difference between memorize and what you did with the state breaking process?
Yeah, right. So memorize isn't it? I was looking up memorize, and somebody says, Haskell is a lazy language. Why doesn't it have memorize built in? Because memorize is really a kind of thing that you would expect to have in a lazy language. So I can just about get away with just using laziness to do state breaking. But I need full memorize to do this as well.
I think there's work on implementing memorize in a generic way, by constructing essentially a trie.
Yeah, I know this. Yeah, okay, yeah. But it doesn't work if your type is a real. If you're memorizing something that's parameterized by real numbers, and I don't think that works in this case. Yeah, no, I understand what you mean. You can convert memorize into laziness if your domain type is count. In this case, the domain type is real numbers, and there's no way to do that, except unless you use some state. Any more questions or ideas? Okay, so let's take a few minutes to recap what we've talked about in this particular course. So in the first lecture, we talked about general purpose probabilistic programming. We saw some examples. Balancing ball, physics and stuff. I wanted to give some references because I didn't give references as I went along. By the way, I don't want you to think that sort of everything I've talked about is my own idea. It's sort of the opposite. I've been trying to tell a story, but a lot of it's coming from other people, whether 100 years ago or 10 years ago or 5 years ago. Then in the second lecture yesterday, we talked about single site metropolis Hastings, and I don't know if this card, here's a guy with a massive hand of cards, it's a very highly multi-dimensional data set, and he's going to pick one at random, and then he's going to switch it. That's how single site metropolis Hastings. A few people have proved it correct. I included a couple of references here, but in different situations. Okay, then in the second lecture yesterday, we looked at probabilistic programs as measures, trying to give a more mathematical meaning to when two probabilistic programs are the same and what they mean. And in order to understand both higher order functions, understand the owner, and also to understand this continuous non-parametric models, where we have some function which, when we don't know what the parameters are, or allow the parameters to change, whether it's the number of breakpoints, whether it's a Gaussian process with an infinite number of parameters. We have this model of quasi-Borel spaces, which we developed, that deals with that quite well. Spaces are just a Cartesian closed category, a model of a functional language with probability. So even if you didn't want to do inference, maybe you want to do differential privacy or something else involving probability and higher order functions, you could use quasi-Borel spaces and everything would work quite well. And then today we've looked at discrete non-parametric models, and we've talked about the Chinese restaurant process. Well, we started out, in the first bit, talking about poly as earn and the beta distribution, and then we pushed towards non-parametric versions of that. And hopefully you can see that by programming gives you an idea of the kind of non-parametric crazy things you could possibly write. Okay, so that's it from me. Thanks.